Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We are pleased to welcome Volker Markl from Technical University in Berlin. Most of you know Volker quite well. He did his PhD with Rudy Bayer many years ago. Then he got distracted and actually worked for IBM. But finally he saw the light and returned to Germany to the Technical University in Berlin. We're pleased to have him here, and he's bringing several students with him. I must be pushing them hard because one of them got a cold and couldn't show up. But two survived. So they're going to give talks, and Volker is going to say a few words about what's included in this presentation.
So thank you for the introduction, Paul, and thanks for the opportunity for all of us to be here with Kostas and Stephan and myself. So I will not talk too much in the beginning because this is really about Kostas and Stephan to present some of the work. Just briefly, the larger context that all of this work operates in. So at TU Berlin, we are conducting research in one major research area that is large-scale data management, massively parallel data processing. And we have a relatively large research project there where now in the order of 12 PhD students are working on actually building a system. So we're doing systems building in a project called Stratosphere, which you also see here. The idea is to build a query processor, parallelize it automatically on a large cluster. And you'll hear a lot about that from Kostas and Stephan. What I just want to briefly mention, though, the original plan was to have two more students of mine here, which we actually had some struggle with, as Paul already had mentioned. So one of my students, Thomas Bodner, he got a flu or cold or something just on the plane or whatnot, and so he is in Seattle, but he is sick today. And the other one, Alexander Alexandrov, he actually had some visa issues and will only arrive tonight because his visa was delayed. So it's a bit unfortunate. So there's two talks which we'll probably talk about next time, or later on after the talks I'll give some brief summary on that. So those talks are, one of them is in big data benchmarking, so a massively parallel data generator where there is some challenges. How can you generate now terabytes or even petabytes of data fast? You have to do it in parallel. And how can you do that with maintaining correlation? So that's one aspect. And the other student, Thomas, his work is on a use case repository for big data. So actually having some, collecting some use cases. We're doing that together with Mike Carey's group at the University of Irvine. So that's the other aspect. So those are two things that I'll be happy to talk about more ad hoc after the presentations. But without much further ado, I would hand over now to Kostas to give a brief overview of Stratosphere and then focus on query optimizations and MapReduce functions, and then Stephan. I should also mention just briefly, so Kostas is so many of you may know him here already. He was interning at Microsoft 2 years ago, and he is a postdoctoral researcher in my group and really driving a lot of the efforts in the Stratosphere project. Stephan is a now fourth-year PhD student who will soon graduate, and he's doing a lot of work in query optimization and in particular parallelization of query processing. And so Kostas, got his PhD with Christian Jensen in Aalborg and was at Microsoft, and now is working here with me, or has been working with me for a little bit more than a year. And Stephan, actually, he did also summer internships at Almaden already, and will probably graduate, hopefully will graduate next year. So with that, I'll hand over to Kostas. Give you this.
Volker for the introduction, and it's thank you for being here. So I will give a brief overview of the Stratosphere system. I'll talk a little bit about the architecture, and then I will dive into some specific aspects of the query optimizer that are quite novel. So they're quite novel in the context of the system. Good. So the motivation of the project as a whole is big data. So we're seeing nowadays huge amounts of data, human generated or machine generated, And at the same time, we also see a need for more complex and more deep queries, so queries that go beyond the traditional data warehousing queries. And this is used in a couple of contexts, so in big science, in business, so people are doing these things. So as a result, over the last couple of years, so a few years by now, we have seen a bunch of completely new systems that are not traditional relational DBMSs, but are used to do this kind of complex analysis. And so one could argue that this really started from Google's MapReduce system, and then we had the Hadoop open source implementation. A couple of more systems in this category is the Asterix Hierarch system at the University of California, Irvine, so at the Mike Harris group, and the Scope system, which is used here in Bing. And the Stratosphere is also one of these systems, and this is the one I will talk about today. So Stratosphere stands from the layer of above the atmosphere, so above the clouds. Good. So the architecture looks like that. So first of all, Stratosphere is a layered system, so there are a few components in the stack, and it actually exposes programming APIs to a few of these components. So on the bottom level, we have a parallel data flow engine, which is called Nefele. So this engine essentially operates on tags that are parallel programs consisting of tasks and channels. We have a layer that does all the query processing, so the join algorithm, sorting, hashing, and so on. And on top of that, we have an optimizer. So an optimizer, the second entry point of the system is what we call a packed program. And then on top of that, one can actually implement languages. So one can implement query languages. And we have a query language called Meteor. And in addition, there is some effort to port a Scala DSL on top of that. So a few words about its component. So the Meteor language is a query language for semi-structured data. So the data model here is essentially JSON. It contains operators to do classic relational processing, and in addition to those, it contains operators to do information extraction, information integration kind of stuff. So this is actually developed at some partners at the Hasso-Plattner Institute that are very interested in doing data cleansing and data mining and so on. Now the packed programming model is essentially a new programming model that is based on and actually extends MapReduce as a programming abstraction. So if you think about MapReduce, there are essentially two second-order functions, and we extend that to provide additional ones. So I will talk in detail about that later. The runtime operators, so the runtime essentially manages memory, it manages I/O, and it has all the usual query processing stuff. The data flow engine gets an abstraction that is a DAG, a parallel DAG, and it does things like resource allocation, scheduling, communication, and so on. And finally, so Stratosphere has a CostBased Optimizer. And this CostBased Optimizer optimizes a packed program, or after a few parsing steps and so on, a Meteor script, and in the future a Scala program. And it picks things like the physical execution strategies, so for example, a sort merge or a hash-based join. It picks things like partitioning strategies, so how will I partition my data? And finally, it picks operator order. So the focus of my talk will be on the Stratosphere Optimizer. Before I get there, so I have a few examples of the queries that you can run. So as I said, we have a JSON data model, and you can write small scripts for rapid processing. So on the top example, we're reading a JSON file and we're filtering. On the bottom example, we're transforming some rows. You can do things like joins. So down here, we're joining to JSON files. And in addition to those, you can actually have user-defined functions. So you can call a user-defined function written in Java. So this is the top example over there. And actually, for most of my talk, I will focus on how to integrate these Java user-defined functions in a CostBased Optimizer.
So is this language It's very similar to Jackal.
Yeah, exactly. So it's very much Jackal. Okay. It's very much Jackal. I forgot to mention that. It's actually, yeah, it's very much Jackal with a few extensions for data cleansing and so on. Now this language is compiled to an intermediate representation that we call Supremo. That stands for Stratosphere Operator and Data Model, which is essentially an operator library with predefined operators that you can actually extend as a user. And these, so just to give you the architectural view, these are then translated into these packed programs. One optimization that you can do there is how to efficiently pack the nested data into records so that you can process them efficiently in the runtime. So the runtime works on a record data model. Now the packed programming model. So the basic idea here is that we have a programming model where you have, so a packed is short for parallelization contract, which is essentially a first order function which is written by the user in Java, wrapped around a second order function signature which is provided by the system, so it is picked by a fixed collection of second order functions. So the basic observation is that the second order function will describe how the data can be grouped into independent subsets which can be processed together. So the observation, and then the user-defined function will be called once for each of these data groups. So the observation was that in the MapReduce paradigm, what we have essentially is a second order function that we call map, right, and a first order function that operates on the record. What the map tells us is that each of these records is an independent subset, and the UDF is called one per subject, so one per record. The reduce essentially tells us that all records that share the value of the key, so here the two records that have a blue key, will be an independent group, and the UDF will operate on these groups. So based on this, you can actually generalize that, and we generalized it to capture a few more relational style processing. So you can, for example, define a cross packed, which is essentially a Cartesian product. So you will get two inputs, and your second order function will take every possible pair of records and create an independent subset for those. You can have something like an equijoin, which we call match. So here you will have a subset, an independent subset for every two records of two inputs that match on the key. And you can call actually UDF on that pair of records. And we have a co-group, which essentially generalizes reduce to two dimensions. So from two data sets, you have a reducer on two data sets. Yeah. So these are fixed. These are hard-coded in the system. So these are the 5 ones that we have up to now, but we're actually interested in looking at others. So one can actually imagine for more packed to do things like stream processing, to do things like similarity joins, and so on. So the packed programming model then essentially is a data flow graph composed of these packets. So we have a direct acyclic graph with input sources, output sinks, and these packed operators that contain a second order function and a first order function. So here, for example, we have two sources that extract two attributes from two text files, for example. We have connected two map operators that do some kind of processing, and then those go to a match packed, which go to a reduce and go to a sync. So one thing to note here is that you're not restricted, as in MapReduce, to have an input source, a map, a reduce, and an output, but you can arbitrarily connect this in any kind of form you want, so as long as it's a DAG. And so another fine point here is that this is a programming model that is exposed to the user. So essentially, you use that to write your UDFs, but it's also currently the intermediate representation that is used by the optimizer to enumerate plans. Now, these packed programs passing through the optimizer create a plan, so a parallel plan that is given to this NFLA data flow engine. So how this looks like is basically a DAG of tasks that are connected by channels. So the fine thing here is that we have 3 kinds of channels. So you have in-memory channels, you have network channels, and you have materialization channels. And what that allows for is pipelining. So you don't always have to materialize data and then read it from disk again. And this gets spanned to a parallel program depending on the degree of parallelism and so on, and is executed in a cluster. So this slide gives sort of an overview of what's happening. So we have a packed program on the left and some user code. This gets compiled to this DAG and some code. So here a hash join is wrapped around the user code, and then some network communication code is wrapped around that, and then given as a task to be executed in parallel. Good. Now we'll move to the main part of my talk. So I will talk about the Stratosphere Optimizer. So we described some aspects of that in a VLDB paper, so 2012, that we called Opening the Black Boxes. So we'll probably see why. So the Stratosphere Optimizer is a cost-based query optimizer that enumerates plans. So currently, it is a bottom-up approach that passes interesting properties top-down. So basically, you are given a packed program, and you generate an equivalent packed program that has a lower cost. And what I will focus on today is a novel aspect, which is how to integrate these MapReduce Java user-defined functions fully into a query optimizer. And the way we did that here, so basically the problem is that you don't have semantics about these UDFs. So what we did is to analyze the user code of these UDFs using a compiler tool, extract a few properties that we can use, and based on these properties, arrive at safe transformations of the plans. So the motivation for doing that is that this programming model that I described is actually quite general. So it's not only used in Stratosphere, but a variation of this model. So a direct acyclic graph of operators that contain this kind of style of UDFs is also used, for example, in Scope. And it's also gaining traction in relational DBMS. So both Greenplum and Aster are trying to integrate and have, to some extent, integrated these MapReduce functions. So it's a timely problem. The problem, as I said, is that you don't know what's inside these functions, so you have to do something about that. And the novel thing about Stratosphere is how to deeply embed those in the optimizer, including reordering them in a plan. So the first step is that you will take each one of those, and you will run a static code analysis tool over them. So we use the Java tool called Suit that operates on some kind of intermediate representation of the Java code. There are also tools for bytecode. So for example, if you don't have the original Java source, you can also do it with bytecode. And what we're going to find is 4 properties of the user function. The first is the output schema. So assuming that we know the schemas of the 2 inputs, we will infer the schema of the output. The second is the read set, which we loosely here defined as what are the attributes of the inputs that may influence somehow the output of the operator. The third is the write set, which is, again, loosely defined what are the attributes of the output that might be different than the corresponding input attribute. Yeah? And the final is the emit cardinality, which says, so per call, how many records are you going to emit? Yeah? So the way to do this is via static code analysis in our case. So here we see an example user function for a match packed, which basically copies out the left input record and has a filter on an attribute of the left record. Based on that, conditional, it either does something using some attribute of the right record, and then does some more things, and it emits a record. So keep in mind that this is a match, right? So this was modeling an equi-join. So the second order function essentially takes every 2 records that match on the key. However, you can put anything you want in there, right? So it's not an equi-join in the sense that you just concatenate the records and emit, but you can really write Java in there. So the important part of this particular Java code is that it's not really general purpose code. So what we have is essentially we have a record data model that we expose to the programmer. And the programmer really has a fixed API for manipulating these records. So for example, in our case, we have an API to create a blank record, to copy a record, to do get set based on field number, and so on. So this is very similar to the PIG API also, and I believe also to Scope with some, I guess, differences. And the final thing is that, remember that the packed program is a data flow. There is really no control flow between 2 operators. So 2 operators can only communicate by exchanging a data set. So you can localize your analysis into each operator. So when you have code with these properties, what you will actually can do is So to approximate the read set, you will go and you will scan all the get statements, right? So from the statements that get an attribute from an input record, you can find out which attributes you're reading. To approximate the write set, what you will actually do is go and look at the set statements, right? So whenever you set something on your output record, you need to check, is that something, so you need to basically reversely follow the data flow graph of the program and look, is that something that could be potentially new, or is it just something that I copy from my input? And if it's something that could be potentially new, then you can add this to your write set. So in this example, for example, if I know that my input 1 had schema ABC and my input 2 had schema DEF, I know my output, and I can approximate by the green statements here the read set, and by the orange statements the write set. And finally, the emit cardinality you can basically approximate by looking at the control flow graph. So you need to look, so here the final emit statement that emits the output record, how many times is it going to be called, right? Is it going to be called 0 to 1 in a conditional? Is it in a loop? And so on. Now, what are the challenges here? So the challenge is how to do this, first of all, correctly, so you don't want to make errors, and how to do this for general code. So the challenge comes from conditionals and loops, so basically when you have different code paths. And there's a very simple solution to that. So in the previous example, we had these statements in line 6 and 7 that are executed only if the condition in line 5 is true, right? However, being that static code analysis, you don't know if that's actually, if this code path is going to be followed. So you have to be safe, and to be safe, you can be conservative. And in our case, we can prove that if these read sets and write sets are bigger than what they actually are, then we will actually get a subset of the correct plans, but all of these plans are correct. So we will lose on optimization opportunities, but we're guaranteed to be correct. So the safe strategy here is, when in doubt, you will always add an attribute to this read and write set, and you can probably get correct transformations. Now, having done that, you can do a couple of things. So first of all, you can pick shipping strategies. So this is the packed program that I had before. So the optimizer knows how to parallelize an operator from the second order function signature. So it knows that for a map operator, for example, is a bar singly parallel. It can run its instance in any node. For a reduce operator, you need to partition the data based on the key. For a match operator, you can do anything that a parallel database does for an equi join. So you can, for example, do a partition join. You can broadcast one side if it's very small, and so on. So based on this second order function signature, the optimizer can pick these shipping strategies. Then based on the read and write sets, the optimizer can actually look if the keys are preserved through functions. So it can identify, for example, a function that preserves the key, so it would not have to do the double work, to partition twice. So here what we see, for example, is that we have done a partitioning on the same key needed by the match and the reduce. So when we are at the time that we need to reduce, we don't need to do anything. So contrary to plain MapReduce, here when you run a reduce, that does not imply a physical sort. A reduce can come for free. The second thing you can do is actually reorder operators. So here, comparing it to the previous plan, I have reordered the reduce and the match pacts. So basically, how you can do that is that you can reorder two map operators if you don't have any read-write or write-write conflicts. So we'll talk about that a little bit later. But the thing is, you can do these things correctly, right? And these things are very important to do. So reordering, apart from decreasing the data volume, can actually give you more opportunities for parallelization, right? Or different opportunities for parallelization. So in this example here, by pushing the reduce down, if the reduce really reduce the data volume, you can switch the build and probe side, for example, right? So very briefly, we can formally prove that we can reorder two map functions if we don't have any write-write or read-write conflicts on their columns. Yeah. So only if you have read-only conflicts, this can be safely reordered. You can reorder a map and a reduce function if that condition is true, and in addition to that, the map function preserves the key groups. So the challenge there is that a reducer expects a certain number of records to be in the same group, and that must be preserved. So for example, if you're trying to reorder reduce with a filter, this filter must either eliminate a whole key group or it must preserve the whole group. So it cannot eliminate some records inside the group. Yeah. And in the paper, actually, we have these kinds of theorems for every pair of pacts. So basically, the map and the reduce are the basic cases, and then the rest of the pacts are derivatives of MapReduce plus Cartesian product and union. So you can do that very easily for the rest. And based on this, you can actually do things like push-down selections. You can do join reordering, so the equivalent join reordering. You can do limited things of aggregation pushdown, so you don't have any semantics about the aggregation done in a reducer. You don't know if that's a sum or something different. But you can if you have some information about keys and foreign keys, you can reorder it with joins. And in addition to this, you can actually reorder reducers with joins for reducers that you would not normally or easily write in SQL. So actually, for programs that you would not typically use SQL for, you can emulate most of the reorderings that the relational optimizer does. Good. So the state of the optimizer right now is that it does the automatic parallelization. The reordering is in a prototypical state, so it was a prototype for the paper. So basically, what that does is that it enumerates all possible plan reorderings, and for each of these, and for each order, it finds the best physical plan. So for the evaluation, we implemented, so we hand-coded 4 tasks in this packed programming model. So we wrote the Java functions ourselves. 2 of these are 2 TPC-8 queries. The third is a pipeline that does text mining. And the final is a simple query that does clickstream processing that has basically a reducer that is not really a SQL aggregation. So the first thing we saw is that the static code analysis finds the correct read and write sets for 3 of the programs. And so basically, it found, using the static code analysis and then enumerating all the plans, we cover 100% of the search space for three of those tasks and 75% of the search space for the other tasks. So it is a lossy analysis, but it mostly has good accuracy. Yep.
Can you be a little, what do you mean by accuracy? I mean, when you say 75%, it's only producing correct results. It's just not covering the search space?
Exactly. So we only get correct results, right? There's no way that you're going to get a wrong result. But what we did was so we ran the static code analysis, and we also hand coded what would be the correct read and write sets.
And so the problem is that
it misses some plans.
And that's because why? Because it saw too large a read.
It found a superset of the absolutely correct read and write set. Right. So what we also found is that if you have an optimizer that can reorder operators, you can get benefits in execution time. So yeah. So in our setting, so this is in a very small cluster of 4 machines. We got a 7 times different for TPC-8 query 7. We got 2 times better plan for clickstream processing, and 10 times better plan for text mining.
Now, for optimization is, of course, generating the plan space, but the other part is selecting the best plan, right?
Right.
So do you have some kind of rough cost model, or do you do only conservative reorderings, or what?
Right. So at this stage, we have a cost model that measures I/O and network I/O. What we did not have is a good selectivity estimation component, right? So we're working on that, and we have a couple of thoughts on how to do that. And this is the reason also that this is not shipped in the open source version. Okay, so some related work. So in the bigger context of big data analytics and query optimization, there are a few systems out there. I talked about a few of them. The techniques that we use to do this static code analysis and reordering operators somehow resemble techniques that were used in the Fortran compilers to do loop optimizations. So there's a small resemblance there. So concurrently to ours, there were a few papers out. So there was a paper from Wisconsin on that did a static code analysis of MapReduce functions to basically find if something is a filter that and then recommend a B-tree index. And we recently found out that people here in Microsoft have been doing similar things. So Scope actually does a static code analysis of these functions. The difference is, from our work, is that you focus more, I guess, on the partitioning side and not on the reordering side, although I may be wrong here. So, Jingren can tell us. But it's interesting, and there are a few things that they do that we do not do. So you can actually do a deeper kind of code analysis. So this read and write sets is a very rough thing. So you can look, for example, if a UDF preserves the sort order of a data set, right, and so on. So this actually, so if you want, so basically to summarize the talk, so I talked a little bit about the architecture of Stratosphere. Stratosphere is a complete new system for big data. So it's written from scratch, and it sort of has the complete stack from processing to query language. It's open source under the Apache license, and it's available at stratosphere.eu. And what I focused on this talk is basically how can you deeply embed this MapReduce style user-defined functions in your query optimizer. The key insights that we got is that, so first of all, you don't need full semantics. A few properties of the UDF are enough to do very powerful transformations. Second, you can accurately estimate this and safely estimate this using static code analysis. And as I said, be always correct. And you can emulate with this most of the transformational power of a relational query optimizer. A few issues of future work. So you can do, as I said, deeper code analysis. You can do transformations that actually go inside the UDF code, so that, for example, slice a function into two or things like that. We are working in the context of the cost model and so on. We are working on doing this, on writing our optimizer in a slightly different way. So we are working on an optimizer that does not try to find the best plan, but tries to find a plan that is good enough under a wide variety of circumstances. So the problem there is that in this cloud setting, you cannot possibly have accurate estimates. I mean, even in the traditional setting, your estimates are usually very off, and here things are even worse. So what we're working on is to basically try to find a plan that works well in a large part of this uncertain space. So robust query optimization. There are a few people that are working on adapting these plans at runtime. So as the characteristics of the machine allocations and so on change, or as you get more information at runtime, change the plan. And Stephan, after me, will talk about how to do iterative programs. So how not to do DAGs, but cyclic graphs, and how to embed that into the query optimizer. Some other interests that I'm having and I'm happy to talk about is actually how to basically integrate all these big data platforms with the new stuff that is happening at the networking layer. So there's actually a big revolution going on in the networks right now with software-defined networking and so on. And this is actually very relevant to us as database researchers and how to go to that space. Good. So these are the papers. And thank you very much. I'll be open for questions.
Again, take one or two specific questions here.
So what version of MapReduce is this working for?
So this is not working. This is not built on MapReduce. This is actually a new code base. So it uses HDFS, the Hadoop distributed file system, to store the data and retrieve the input data. So you can use that, but it doesn't have any common code with Hadoop.
Are you thinking about maybe for Hadoop 2.0 with Yarn?
Yep.
Where there's going to have allow different types of programming frameworks? Are you thinking about?
Yes, we are thinking about that. We are thinking about porting it to Yarn, so that people can try it out very easily.
So if I can follow up on that. So one key aspect of that parallel data flow engine that was just at the bottom was that it has a very flexible scheduling model, and it was designed to run on infrastructure as a service cloud, so it's actually able to have just a single master running and then allocate workers on the fly for its tasks and deallocate them while parts of the data flow are still running. So that was built into the core design, and so we're at the moment, we have a student that is trying to replace that connection to the infrastructure as a service controller with an interface to the Yarn resource manager, so it's allocating instances for Yarn. So because it's more or less following the same principle. Yeah.
So when you did the Java code analysis, so do you use any kind of the Java kind of the tools to do that, or you write your own program to do it?
So we use the tool. We didn't write our own static code analyzer. The tool is called Suit. So it operates on a 3-address code abstraction.
Okay, thank you.
Thank you.
All right. Okay. So yeah, this talk is more or less going to seamlessly follow up on what Kostas did. So it's it's in the context of the same system, and as Kostas mentioned, it's basically the techniques we included to make the system an efficient runtime for algorithms that are iterative in nature. And yeah, I don't think I have to do a big motivation for that, because I mean, iterative algorithms are everywhere when it comes to machine learning or data mining. So the people that have played with Hadoop or with MapReduce for iterative programs probably know that, I mean, you can do it. You can always write a driver around a MapReduce program and invoke it time after time, and it's not doing great. And there have been modifications of Hadoop that try to overcome that. And they have been doing a little better, but still not great. So we're presenting the techniques that we have developed to actually make that a little better. And the motivation for the whole setup is the following. With Hadoop and a lot of those other general purpose big data analysis systems not being great at running those machine learning algorithms, those iterative algorithms in general, there's been actually a variety of dedicated or specialized systems for iterative data processing. So Google has published a paper about Pregel, which is this bulk synchronous processing adaptation for graph analysis. There's, of course, as always, an Apache open source version of that. There's been the GraphLab system by people from, I think, shared from Berkeley and Carnegie Mellon. And they're dedicated systems that try to overcome the problem that the general purpose big data analysis systems are not really doing great at those iterative algorithms. But the problem that a lot of people are seeing today is if you're running that actually in a production setting, and assume you're doing things like training a spam detector or a recommender on a periodic base, what you typically have is the data is not in the format that you can just throw it into your graph analysis algorithm. You typically have something like Hadoop, or you can replace Hadoop here with Stratosphere, or maybe your favorite data warehouse, to actually extract the features or the data from your sources, transform it into a format, probably normalize it. Then you throw it into this specialized system for iterative data processing. Then you take the result, you actually post-process it, maybe map it back to the keys you use in your production system, and so on. So you actually have a rather complex processing pipeline. And this is basically all because the systems you use for the first and the last step, which are typically general-purpose data flow systems, or MapReduce or a parallel database, are not really good at those iterative algorithms. So the idea was, if we could just make the data flow systems good at this step in the middle, then we can actually simplify the whole process by a lot. And for a lot of reasons, we think that just making a data flow API able to process iterative algorithms efficiently is a very worthwhile thing. So first of all, you actually see that a lot of those specialized systems are very specially tailored towards certain use cases. And if you use a data flow API, with some extensions, those are very flexible. This is a very flexible model. So as you will see in the later part of the talk, we can layer custom APIs on top of that very easily. They typically correspond to just a very special data flow. So Pregel is a special case of an iterative data flow, as we're going to present it later. You can also add compile DSL scripts to that very easily, or you can program directly against that, like people are programming against MapReduce. So, I mean, if you think about making data flows iteratively, the first thing you need is actually not so complicated. So let me motivate that with an example. This is an implementation of the PageRank as it looks like in Stratosphere. So you can think of match here or join. I put join because it's easy. It's more commonly understood actually. And PageRank is just an iterative matrix vector multiplication where the vector is actually a vector of ranks for each page, and the matrix is the, if you wish, the topology of the network with transition probabilities of the edges. And what you do in each step is you actually join first the current rank vector with the matrix, and then you aggregate the rank for the page in the reducer. So we represent that in a data flow. The rank vector as a pair of page IDs and ranks over each page, the current rank, and the transition matrix as a pair of triples. The matrix is actually very sparse. A lot of pairs of pages don't have edges between them. So the transition probability is 0, and we just skip the entry from the matrix to represent it in the sparse way. So the matrix is here just a set of triples: source page ID, target page ID, and some transition probability. And then the algorithm is just joining them and aggregating that. Okay, so if you want to make that iterative, you can always say, okay, let's just run that one again and make sure that the next iteration consumes the output of the previous iteration. You can emulate that by just renaming the input files or so, or you can just say, okay, let's include a physical feedback edge in the system. So that's actually a pretty simple idea, and it helps a bit. But if you run that repeatedly, you'll actually see that it is a lot of redundant work. For example, it's going to do all the full processing of the join of that input, which it actually doesn't need to. That is something that has motivated some of the specializations of Hadoop for iterative processing. For those of you who are familiar, for example, with the Hadoop or the Twister system, what they did was, for example, they gave you the ability to say, okay, here is a loop invariant data set for the reducer that would then be partitioned and sorted only once and then cached in that variant. So that is something that is actually very neat, but of course, we have our general purpose data flow system, we have an optimizer, so let's just have the optimizer do that. And the thing to do that is actually very simple. You just have to identify in this data flow a difference between the dynamic path, which is everything that is basically a successor in the cyclic flow of the feedback edge, and the static path, which is basically everything that's not a successor. And we enabled the runtime to actually basically cache the data set where the constant and dynamic data path meet. And caching is just something like placing a temp table, or actually it doesn't really need to be a temporary table, but if the join is, for example, using a hash table, you can just make that hash table persistent across iterations. Something like that. And then we just gave the optimizer a notion of this constant and dynamic data path and gave the costs a little different weight. So the costs of the dynamic data path are weighted more than on the constant data path. And what comes out of that is actually immediately very nice. So we'll see that it comes up with plans that try to push work into the constant data path and cache the result. So those are two different query execution plans for this PageRank algorithm. I mean, the database people will immediately see the difference between a broadcast join and partition join. The interesting thing is, if you look at those two variants, they're actually two very famous hand-optimized variants. The left one, the one that has been in Mahout for quite a while, optimized for computing the PageRank of setups where the rank vector actually can be broadcasted. And the right one is the one that is close to the execution strategy that Google described in its MapReduce paper. So the optimizer just gives you those two variants depending on the size of the rank vector. So that's all fine. That's an easy win. Okay, that's the summary. So all you need to do is actually make the optimizer aware of a feedback edge, of a constant data path, dynamic data path, and different weights. So there's a class of algorithms that is still doing kind of suboptimal in that setup. And let me motivate that with a very simple algorithm here. That is an algorithm taken from the Pegasus paper, Foluzzo's paper on graph analysis. It's an algorithm that finds connected components of graphs, and it does that in a very simple way by saying, okay, each vertex is assigned a component ID, and after the algorithm is run, all vertices that are in the same connected component should end up with the same connected component ID. So this algorithm iteratively just takes the component ID from each vertex, tells it to all of the vertex's neighbors, and each of the neighbors just says, okay, if I find an ID that is smaller than my own current one, then I'm going to take that one, and I go on. So you can actually see that after a few iterations, all vertices in the same connected component end up with the ID of the vertex with the smallest ID. And I've colored the vertices in that example a little differently. And the reason behind that is the following. Not in every step will every vertex end up with a new ID. And if a vertex doesn't end up with a new ID, then basically for that vertex nothing changed. So there's no need to really take the information of that vertex and incorporate it into the next iteration, right? So this is a phenomenon that is often called sparse computational dependencies. It's especially present in graphs, but also in a lot of other problems that can be modeled as graphs. So you really want to take those into account. You can always run an algorithm like that in the fashion as we had it before. So you can model this connected component algorithm actually in a very similar way. You can model it differently, but I just modeled it the same way with a join and a reduce. A join, again, between the vector that represents the state of the vertices, in this case, just vertex ID and component ID. And the matrix is now even simpler. It's just the edges, right? And you, again, joining meaning every vertex tells basically the end of its outgoing edges about its component ID, and then do a minimal aggregation of all the candidates. So if you run the algorithm like that, you'll actually see that it does a constant amount of work in every iteration, right? Because it fully recomputes the entire next state. It consumes the previous model entirely, and it recomputes a complete new version of it. And it will, in a lot of cases, end up recomputing just the same state as was the input to the iteration. If you look at the green curve, this one is actually the number of vertices that really changed in each iteration, so that contributed something, or that would contribute some new information potentially to the next iteration. This is the ones that were colored red in the previous example. So this is very true for many algorithms, that you see actually that the number of vertices that contribute is going down after a few iterations. That is not only true for something like connected components or finding shortest paths, but it's also true for modified versions of PageRank that try to adaptively schedule the computation. And the difference in the work you do in each iteration is, of course, huge. So exploiting that is very desirable. So how do we actually do that in our system? Because it's a property of data flow systems, actually, that each operator's result depends only on its inputs, right? So they're kind of a natural match for this bulk version of iterative processing. And this was one of the main motivators actually for Google's Pregel system, because there you can really keep the state of a vertex across iterations. So how can we try and encapsulate that still in a very generic fashion to embed it into a data flow? And yeah, one thing was that we said, okay, we actually need two representations of data flows in our system. We have the bulk representation, which was the one I just showed you before, the rather straightforward one. And we have an incremental type of iterations where you try to encapsulate exactly that nature, that only parts of the model change. You'll later see that there's actually a special case of those incremental iterations that you can even run without the typical super step synchronization, which you have in most systems after each iteration. Okay, so the abstraction that we picked for representing that in a data flow is called a Workset Set Algorithm abstraction. Workset algorithms are a technique actually from compiler construction, and it's used there for optimizing loops. And so that was actually intuitively a good match. It's used to optimize loops to have them incrementally compute the next element that they work on. And you can think of that actually as if you know semi-naive valuation and recursive computation, then Workset algorithms is on the same level for iterative computation. So it's a very similar thing. So what we're trying to do is, or what we're giving here the system is an abstraction that is not working on a solution set, on a single set that it's recomputing every time, but it's actually working on a work set that it's recomputing every time, and instead of computing a new solution set, it's out of the work set computing a delta for the solution set, and then using this delta on the previous work set to compute a new work set. So you typically model the algorithm in that way, that the work set is candidate elements that go into the delta, and with the delta and the previous work set, you compute new candidates. So if you want, here's a brief illustration of this connected components algorithm in the work set. This is our solution set here, really. The state of the vertices, and the work set is the candidate component IDs for the work set. So I modeled it like this, that it's basically grouped as it goes into the reducer by the target vertex. So vertex 1 here really gets from vertex 2 a candidate component ID of 2, and from vertex 3 candidate component ID of 3. And similarly, vertex 6 gets candidate 5 from vertex 5. So what you do with that is you actually compute a delta for the solution set, which you merge into the solution set, and then you take those two to compute a new work set. With that, you actually get a new delta you merge into the solution set. And you actually see that the work set is typically going down. So the termination criterion for a work set algorithm is really the empty work set, actually. Similar as for a recursive algorithm in same-naive evaluation, it's if no rule derivation is added. Okay, and this really encapsulates this dynamic computation scheduling. So if we want to represent this as an iterative data flow, we actually see we have a feedback edge from the next iteration's work set back into the system, and a delta which goes as not really as a union, but as a modified union operation back into the solution set. And this algorithm is now very similar. It's just the join is basically still the join you had in the algorithm before between the edges, and in this case not the entire solution, but basically what came out of that operation, which also goes into the delta. And this is the reducer. So the co-group, as Kostas mentioned, is a more-dimensional reducer, which is in this case not reducing entirely on the work set, but also comparing that to the solution set to actually compute a proper delta. And yeah, so interestingly, you can more or less take this plan as being a template to implement any Pregel algorithm. So I said before, if you use such a more flexible abstraction, you will actually see that a lot of the specialized systems are just special case data flows on top of that abstraction. So this is basically the abstraction to do Pregel on top of that. I mentioned also earlier, which might be interesting to note, that in some cases you can eliminate the superstep barriers here. So this is the same plan as we did before for this incremental algorithm, but the difference is now that we don't use a co-group here. Remember, co-group, like reduce, is a group at a time operation. We replace that now by a tuple at a time join operation. So what we're doing in this case is really we're taking not the entire work set and combine it with the solution set, but we're taking one element at a time out of the work set, if you wish, and comparing that to and taking this candidate and seeing whether it actually should affect the solution set. And the reason why we can do that is because in this special algorithm, we actually have an idempotent operation in here, basically selecting the minimum one, the smaller one of the current state of the solution set and the new candidate ID. And because you don't need to do this on the whole group at a time, you can just do that on the elements individually. So if the algorithm actually has idempotent, or it doesn't necessarily have to be idempotent, but there are also weaker conditions which hold. If the algorithm fulfills that condition, you can actually often transform the group at a time operations to tuple at a time operations, and then if you have only tuple at a time operations, you can eliminate the superstep boundaries and let the algorithm run in a basically unsynchronized fashion, more or less. Okay, one last interesting thing that I want to point out here is with that abstraction, you can actually do algorithms that, for example, Pregel cannot do. So I said earlier that there is an interesting variant of the PageRank algorithm. It's called adaptive PageRank, which tries to exploit the dynamic computation and built on the fact that actually the pages that end up with a very small rank typically converge very fast to the small rank. And most of the later iteration actually work only on both on the high rank pages and on the pages that take actually special roads like hubs or so between densely connected components. That one's actually implemented on Pregel just in a very hard fashion, but in this case it's just another special case of a data flow. So it's a pretty versatile abstraction that allows to do quite a bit. A few performance numbers on on how we did with that. So we compared our implementation of bulk algorithms, which is the first version, just with a naive single feedback edge, with an implementation of the iterative algorithm, and also here one with the elimination of the superstep boundaries. We compared that to Giraffe, which is this specialized system for graph analysis, and Spark. So Spark is a pretty neat implementation, actually, of a data flow system that's very good at doing those bulk iterations. And we ran that on 4 different graphs. And so one thing that's actually visible directly is that the systems that can exploit the sparse computational dependencies are always faster than the other ones. It seems that our bulk processing and Spark's bulk processing are, let's say, in the same order of speed. And the incremental processing is actually competitive with the specialized implementation on Giraffe. On the larger data sets, we actually could only do an implementation of the algorithms against our own between our own different modes of execution. And the problem is the following. So our cluster is actually not that big. Some of the data sets are actually pretty big. So with the generated candidates and so on, you actually create intermediate data volumes that are exceeding the size of the main memory. And because this is really just a special case of a data flow with all the algorithms implemented in such a way that they operate well under memory pressure. I mean, the join just degrades to disk, right? The sort becomes external, and so on. It just worked, whereas both Giraffe and Spark actually being actually special talent and not building on top of the previous existing implementations of those algorithms as they're known from literature. Those systems actually were not able to handle it, at least in their current point of implementation, at their current implementation state. They were not able to handle those larger sets.
Question.
Yeah.
Why the incremental versions is more expensive than the purple one? What is the purple one?
This one here?
Yeah.
This one is the one without the superstep boundaries. This one is the one with superstep boundaries. So, okay, why that one is more expensive? Let me go back to that plan. Here, okay. So if you look at the way this one executes, it's basically taking the smallest of the candidates, comparing that against the current component ID of that vertex, and only if that one is smaller, it puts it into the delta and into the join that creates the new candidates. If you look at this one here, maybe this is taking at first only second smallest one, updating it with the second smallest value, and then it's creating candidates based on the second smallest value, and then it's actually updating the state to the smallest value, so it's creating new candidates based on the smallest component ID. So the candidates based on the second smallest component ID will actually have no effect in the end, but they're still actually processed in the system. So depending on the structure of the graph, that may sometimes be more expensive. It may sometimes be cheaper. So this is something we actually saw here, that it can make a difference sometimes. In general, so we have to actually, this is some of the follow-up work. We have to investigate that a little more. The ability to run algorithms asynchronously actually opens a very different realm of doing it, which we have not yet explored. We assume actually that they are more robust to processing in the presence of, let's say, stragglers and slowed down nodes, because you don't have to globally synchronize at each step. But that is something we're actually currently exploring. So at this point, I just want to point out that it's actually possible to run that model. The true benefit of that is something we're currently investigating. Okay, a bit of related work on that. So I mentioned before that there were adaptations of Hadoop and or MapReduce in general to make it run bulk iterative algorithms efficiently. And the optimizations they put in there are actually mostly subsumed by the optimizations that the optimizer does here. There's the bulk synchronous parallel processing model and its adoptions, Pregel and Giraffe, which are actually just special cases of the incremental iterations that we showed here. An interesting parallel work on that was by people from the former Yahoo group, so Raghu Ramakrishnan's group, which is now here, and UCI, Mike Carey's group, which they came onto, or they stumbled into very similar observations of problems, and what they did is they tried to model it exactly in the recursive way. So, I mean, recursion and iteration is theoretically equally powerful, so you can build from both actually an abstraction for that. They they compile recursive definitions of the problems down to data flows, which is actually possible. At the moment, I think actually that the abstraction that we have here might be somehow simpler even a bit, because in the recursive rule expression you have to include certain tricks like temporal variables to actually say, okay, this rule derivation is actually a new version of the old rule derivation and so on. But it's in general equally powerful. And then there's the specialized system GraphLab, which I think is of all the specialized systems currently most interesting one. And so you can actually model the GraphLab processing almost as a special case of a parallel data flow, the only thing that GraphLab at the moment does. So GraphLab allows to work asynchronously, which we also do, but they have a special way of being able to relax consistency constraints, because a lot of the algorithms are numerically stable enough to still work under relaxed consistency, which we don't allow at the moment. So, but there's we're actually looking at how it's actually possible to tell a system that only relaxed consistency is necessary here. Okay. So yeah, that's the second part of the talk, and yeah, to conclude it, actually, integrating iterative algorithms into a data flow is a very worthwhile thing, because it can actually subsume a lot of specialized system and can lead to homogeneous data processing pipelines, and exploiting sparse computational dependencies and dynamic scheduling is something that is very important to do, and Workset algorithms, or the Workset abstraction is actually a way to do that without violating the principles of data flow programming, like side effect-free operators. And if you integrate that properly, you can actually end up being very competitive to specialized systems. Okay, so that's it. Thank you.
Thank you.
Two questions.
Yeah.
What is the optimizer's role in the iteration? So do we optimize different iteration with different plan, or it's a static plan?
Yeah. Okay, that's very interesting. So the feedback at your model doesn't necessarily really have to be a physical feedback channel. It can just be logical, and you really unroll the loop basically lazily in the processing, and that would actually enable you to easily use different plans in each iteration. So. We're not doing this at the moment. We're at the moment optimizing with the expected costs for the first iteration. There are, of course, cases where the size of the partial solution changes, especially if you have like inflationary fixed points or so. And yeah, it's definitely worthwhile to look at that. We have not done that at this point. So the system is theoretically able to handle that, but we've not yet done the incremental optimization aspect of it.
The second question is that in the setting of the large cluster, machine can come and go.
Yeah.
And you cache data, and what if the machine goes down and you cache the...
Okay, so
how did you revoke, and how did you restart recompute the thing that is in the cache?
So the cache is basically at the end of the static data path. So okay, at the moment, when what we're doing is when a node goes down, we're assuming that we can actually allocate a backup node for that. So what we're not doing is, if we start on 10 nodes and we hashed everything into 10 partitions, that we do a rehash into 9 partitions or so, because that would actually mess up the cache. That is true. As soon as you can allocate a new node, which actually takes over that partition, then you actually do the fault tolerance recovery just as in the non-iterative part, because it's part of the static data path. You redo some work. Actually doing recovery and fault tolerance in a system where operators have not the blocking property is a very interesting problem of its own, and on which the people in our research group that are building the parallel data flow engine are working on. So I can tell you a little about that offline if you're interested in that, but actually this works very transparently here for this part. With the limitation that you need a backup node, you don't redistribute it among a smaller set of nodes, so at the moment. Yeah, Chigman, please.
To follow up with this question. So try to understand what is the role in this case for the optimators. Looks like the optimators just add the cache operators, try to decide where to place the cache. Everything else will just happen automatically.
The optimizer basically does what exactly Kostas described, And in addition, it uses a heuristic to place the cache. And yeah, as I said, the optimizer doesn't really need to be changed all that much, except that you need to tell it to identify the dynamic and constant path and actually use different cost weights. Everything else is almost given for free because it's the regular operation of what the optimizer does anyways. So there's, I think, a slight difference in the way that the optimizer works at the moment in our system compared to the classical Volcano-style optimizer. And that is that interesting properties when they're propagated top-down are not only used actually in the pruning phase, where you say, okay, I keep a plan that is slightly more expensive around if it fulfills an interesting property, but it's really also used to generate candidates that actually realize strategies further down in the plan than they're actually needed. So this is the way how the work actually ends up further down below in the constant data path. But that's the only difference, I think, to the classical Volcano model here.
The introduction of the cache operator is based on heuristic. I assume that it's probably you have to identify the loop and then have some kind of heuristic to consider whether to add cache or not cache.
Yeah, so at the moment we actually cache always at the point where the constant or dynamic data path mean, and we just place the cache either, you see in that case actually after the build hash table, so it caches the hash table as a whole. The hash table just becomes persistent across nodes, and yeah, this is a probing operation. I mean, this is not really an operation. It's just added in this visualization to illustrate that what the plan does. So the cache is actually after the latest operator that really changes the data at this point here.
In principle, you can basically let the optimizer optimize the plan as it would normally do. So you have to give a little bit more weight to the dynamic data path, but in principle you could do things like pulling things out of an iteration, pushing things inside an iteration, so on.
But going back to the question, so however, there's heuristic that are used for generating the plan candidates, and that those heuristics would decide where the cache operation would be. And Stephan just gave the simple heuristic, which is whenever the dynamic data path here comes in and meets with the static data path, that's where a cache operator is placed.
So I'm not sure if you're maybe referring to optimization rules. There's things like this magic set transformation, which try to actually pushes filters from a somehow successive iteration into a previous iteration. And so those are, I mean, this is something that you could add. This has been added to the optimizer of a relational database, and relational databases, if you wish, an optimizer similar to this one as well. The problem that we're always having here is that you're operating on a restricted set of semantics or a smaller set of semantics, so sometimes those optimizations are a little harder to apply. But if you follow up the project in the next year, you'll actually see that we're moving to a semantically richer model. So I think then it'd be able.
Iteration opens up quite a lot of interesting optimization issues. No question about lots of things that you can do. All right, any other questions? Not related to optimization. All right, thank you, Stephan.
All right, thanks for listening.